we've been talking about movement of molecules from regions of higher activity to regions of lower activity. Now, molecules can also move, or rather substances can also move through membranes as well. Osmosis is defined as movement of solvent, such as water, across a membrane from region of higher molecular activity to regions of lower molecular activity. So we looked at diffusion across cell membranes in Melodia, which we looked at previously. It's an aquatic plant. So first off, we're going to look at normal Melodia. Not a very good slide. Take a look. Melodia is pretty normal. You got your cell walls here, and cells full of lots of little green chloroplasts. Not a very clear slide, but that's Melodia. It looks totally normal. Now what we're going to do is I'm going to add salt water to our Melodia. And this salt water is going to cause osmosis to occur across our cell membranes. Okay, looks like it's already occurred. Now, when osmosis occurs, that is when the solvent moves across the membrane, it always moves from a region of higher concentrations of solvent to lower concentrations of solvent. So it moves from areas where there's less solute to more solute. Basically, it moves from areas that are wetter to areas that are drier. So previously, your Melodia looked pretty normal. And now our Melodia cells have been plasmolized because our Melodia cells have high concentrations of, or rather, we have two sides of our membrane. We've got inside the Melodia cells and outside the Melodia cells. Inside the Melodia cells, where there is lots and lots of solvent, it's called hypotonic. Outside the Melodia cells, you have high concentrations of salt water, which has very low concentrations of solvent. So it's very hypertonic. Water always flows from a hypotonic environment to a hypertonic environment. So water is flowed from our hypotonic cell to our hypertonic solution outside. So you can see our Melodia cells have been plasmolized. As water rushes out of the Melodia cells, they change. They've got a rigid cell wall, so the entire cell is not going to shrivel up, but the plasma membrane inside that cell wall is going to shrivel up. And you can see it looks kind of like a plastic bag crumpled up inside the cell, because the plasma membrane has been detached from the cell wall, shrivels up and pulls away from the cell wall. Becomes visible. So that's plasmolysis in Melodia. If we add distilled water, the process should reverse itself, and the cell should look normal again, and that's called deplasmolysis. But I'm not going to show it to you today because it takes a while to come into effect. Now we're going to take a look at our final set of exercises. Okay, our next set of exercises are demonstrating dialysis in non-living systems. You have probably heard about dialysis before. Now, in medicine, we use dialysis for people who have kidney problems. They can take a person's blood out of their body and run it through a cellulose acetate tube, and that tube's got very small pores in it. And the waste in their body will diffuse through the pores and dissolve in the solution. The red blood cells are too big to go through the pores, and so they get returned to the body. So dialysis is movement of a solvent or a solute through a membrane as long as the membrane has pores that are big enough to allow the substance to pass through. Basically, things that are too big will not be unable to fit through the pores. So it's got a very crucial difference between osmosis in that you can have solutes or solvents, not just solvents only passing through the membrane. Remember, osmosis was movement of a solvent only. But now solutes can move through the membrane too. So I've got water here. In this water I've added sodium hydroxide. Sodium hydroxide is lye. It's a very basic solution. I've got phenolphthalein. Phenolphthalein is a pH indicator, so it changes color when the pH changes. So I'm going to add phenolphthalein inside our dialysis membrane. So I've got a pH indicator inside the membrane, and I'm going to place my dialysis membrane inside our basic water. We're going to look for a color change because we want to decide what can fit through the membrane. Is the hydroxide ion small enough to go in? Is the phenolphthalein small enough to leave? Or are they both small enough to fit through? And as you can see, we've got a pink color inside the bag. The pink color inside the bag means that hydroxide ions are small enough to fit through the membrane holes. And we don't see the pink color outside the bag because the phenolphthalein is too big to fit through the membrane. So hydroxide is small enough to enter, phenolphthalein is too big to leave. That's when we see the color inside the bag. So that's dialysis with phenolphthalein hydroxide. Now, we've got another very similar experiment with dialysis. And now I've got a starch solution inside my beaker. So I bet you can guess what I'm going to put inside my bag. It's going to be iodine. So we're going to have iodine inside our bag and starch in the solution. We want to see if the iodine is small enough to go through the pores, is it too big? Starch small enough to go through the pores, or is it too big? I want you to remember that starch is a polysaccharide, right? So it's a very large compound. Poly means many, because it has many sugar rings attached to each other. So we can predict pretty easily that starch is going to be too big to fit through the pores. Probably. So we'll see if the iodine is small enough to enter. So we've got iodine in our bag, and we're looking for the presence of that blue or purple color that always occurs when starch and iodine meet. All right, obviously, we've got iodine leaving the bag because it's small enough to fit. Let's take a look and see if we have any starch entering the bag. You can see the iodine has stayed brown. That means the iodine is too small, or excuse me, the starch is too big to enter the bag. The iodine was small enough to leave. The iodine didn't change color inside the bag. Okay, so we've got a couple of related concepts. Brownian movement. Brownian movement is movement of small particles caused by random movement of molecules. We saw that by looking at the random movement of the black. And this random movement of molecules causes all the rest of the phenomenon. It causes diffusion, osmosis, and dialysis. Remember, diffusion is movement of molecules from regions of higher molecular activity to regions of lower molecular activity. And it's influenced by temperature. Colder things diffuse more slowly. It's influenced by viscosity. You have lower rates of diffusion and more things that are more viscous. And it's also influenced by concentration. Things that are higher concentration diffuse more quickly. Also, it's influenced by molecular weight. Things that are heavier diffuse more slowly. And we also talked about osmosis. Osmosis is movement of a solvent through a membrane. And remember, osmosis, the solvent always moves from a region of more solvent to less. That is, it moves from a wet region to a dry region. That is, it moves from a hypotonic region to a hypertonic region. And we saw osmosis in cell membranes below you. We saw plasmolysis of the cell when it was placed in salty water as well. Finally, we looked at dialysis. Remember, dialysis is movement of a solute or a solvent, that is, it could be either one, through a membrane as long as the molecules are small.